Cellular automata. CA are computer simulations that try to emulate the way that laws of nature are supposed to work. They can help us explore if the reductionist approach that scientific research has taken is actually realistic. But can we really imagine that those fascinating, complex, and seemingly random words, as created by a small set of relatively simple rules, are representing nature? CA can never give definitive answer to this question, but they can give us an idea of how reasonable the thought of a world governed by simple rules is. Let's start with a one-dimensional CA, 1D CA. A one-dimensional cellular automata can be thought of a finite row of squares. Each square has a neighboring square to its left and a square to its right. Each square is called a cell. Each cell can be any finite number of states during each unit of time. For example, off and on in the case of binary strings that we are going to use in our examples. So here we have a cell, another to the left and another to the right. The state that a particular cell is in is determined by a set of rules which depend on what state the cell is currently in. This is the current state of the state, this, and so forth. What the state of its neighbor, for this case, the central cell is 1, his left neighbor is 1, his right neighbor is 1, and in the next step he will remain 1. In this case, the cell current state is 0, the left neighbor is 1, the right neighbor is 1, in the next generation he will be converted into a 1. In this case, the cell is 0, both his neighbors are 0, and he will remain 0 in the next step. Just to get an idea, now let us see a CA developing through several generations. Let's try the CA rule, CAR 254, which is seen here below. We are using the same 254 rules that we have seen before, so let's see what will happen with the first generation to come. See, every time a window of 3 is moved along the line, and accordingly to the rule, the central cell is changed. In this case, a single live cell changed into 3-1. Now we have another run, and it looks a little bit different. Instead of having a configuration of 1-1-1, we have now 1-1-0-1-1, which is completely another pattern. Let's try and see what's happening now. In this case, we got a continuous string of ones. And the new word is replacing what we called the word. Let's do another run in which we'll see another change, and we'll finish yet with still another run with another change. Please note that every time that a new pattern is created, it is moved to the upper position. This will be our last run, and we got this pattern. I do hope that we understand the idea behind the pattern generation. Now that we have a feel for how a computation works for a one-dimensional CA, let's try to figure out how many different kinds of 1CA there are and try to come up with a nomenclature for these rules. Since each cell can be either on or off in this binary string of ours, there are 2 multiplied by 2 multiplied by 2, or 2 to the third, which are 8 different configurations possible. Thus, With 8 cells in a row, there are 2 to the power of 8, or 256 different rules possible. Wolfram's came out with a numerical tool, and since there are 256 possible CAR, we can assign a unique number between 1 and 256 to a card that also encodes the rule. Stefan Wolfram has came up with a naming convention for the 1D CA. Look at the 8 cells below the triplet. As we move from left to right, we consider whether a cell is on or off, on, off, on, off, on, off, on, off. We'll generate a string of 0 and 1s of length 8 from each cell. So for example, the string 0, 1, 1, 0, 1, 0, 1, 0 corresponding to the rule whose first lower cell is off, the second is on, and so forth. Of course, the upper triplets always are expressed in the same order. In base 2 mathematics, this binary string corresponds to the base 10 number 106, because this is 2, this is 8, this is 32, this is 64, and adding them together we get the number 106, so the car will be assigned the number 106. We now use another program to generate many generations of 1DCA while keeping and displaying all the previous generations and not showing just one at a time like we did in the previous program. Using this program, we will be able to examine several CA rules. The first one, specified here on the live, defines 6 out of the 8 cases in which the central cell will be either kept alive or made alive regardless of what is the status of its neighbor. The 2 other cases, the first one, the central cell is kept dead because both his neighbors are dead, and in the last one he's moving from a state of life to a state of dead because of his 2 neighbors which are alive. Let's run and see what we are getting. This is a generation after generation accumulating together, and this is one of the most famous pictures in Cellular Automata. But now let's try and change some of the rule. Let's change this rule from alive to dead, meaning that the central cell in the next generation will die, and running it we get a completely other pattern. Let's change another one, for instance that, from alive to dead, and running it we get a very uninteresting line.